Hello, welcome to another video in this big O notation series. And in this video, we are going to talk about the criteria you will see that gives you that opportunity to understand the right time complexity of a code. So the first big O notation we'll be talking about is the constant time, which is the big O of 1. So what are the criteria you will see in code that will give you that understanding that this code is big O of 1 constant time? All right, so the first criteria you will see is what? Fixed number of operation. So if you go to our VS Code and you will see we have this function which is sum two numbers. Now it takes in number one and number two. So what the function does is what? It's returning number one and number two. While at the bottom here, we are invoking that function. So the process of this function, it is what? Big O of one time complexity. So the reason is because this is what? A fixed time operation. So another criteria you will see is accessing item in a data structure such as list, object, and dictionary using a key or an index. All right, let me look for a closer example. Okay, yes, look at this. It says get first element. So this function takes in a list. This function takes in a list, and what this function is doing is returning the first item in a list using what? An index. So there is no loop, there is no map, there is no filter. What is going on here is using a fixed index. So when you are using a key or an index in an object to access a particular item, that operation is known as big O of 1. Right, so the next example or the next criteria is the code does not depend on the input size if there is a loop. All right, most people do say when you see a loop, you should know that the code is big O of n. That is not necessarily correct. So I'm going to give an example, right? Let me give an example. So I'm going to give an example of a function that that takes in a list, for example. Okay, this function taking a list, and what we are going to do is loop through that list. Okay, I think I already have a list here. Okay, good. So now if we invoke this function, we need to pass in a list. The fact that this function can do without the input, this function, the algorithm is regarded as big O of 1, which is constant time. So the code does not depend on the input of this function. It does not depend on the input size, right? So it can accept a value like this example we use here. It can accept a value, but it does not depend on the size. So either you pass in 10,000, 1 million, 1 billion, it doesn't depend on the size of the input. All right, the takeaway here is an algorithm with big O of constant time can also have a loop, right? It can also have a loop in between. Let me give another example quickly. Okay, so an algorithm can also have a loop, but this can even be 1,000. This can be 1,000. This can even be 10,000. This can be 10,000. But the fact that this algorithm does not depend on the input size, it is regarded as constant time, which is the big O of 1. Next, we want to identify the big O of n, which is the linear time complexity in code. So what are the criteria you see? The first criteria you see is a single loop. that depends on the input size. Let me go to my VS Code. And if you look at the example I have here, I have a function here which is print all. And this function has an input which is an array. So what is going on here is the function is looping every item in the array and printing out the item. So you will notice that this algorithm depends on the input size. So when you see a things like this, when you see a code like this that has an input and the algorithm is dependent on the input, this algorithm is can be defined as big O of n. So another things you will notice here is inside the loop, there are no operations greater than constant time. So what they are trying to tell us that inside this loop, there is no further operation like another loop, right? Like another loop like this. Okay, sorry about that. There is no such operation like another loop. Okay, so it's just a single loop, and in that single loop there shouldn't be an operation that is greater than big O of 1. So another thing you will notice that this operation cannot do with the array, right? So it depends solemnly on the array. So it depends on the input size. You can see we are printing out every item in the array. So this is depending on what? The input size. So another example include iteration over a loop. I think this is just straightforward. So we've covered that already. This is an iteration. So what iteration is counting an element and make sure you count every element in an item or every element in a list. So this is what ignore constant, and the reason I include ignore constant to the list is there may be some cases whereby we have something like this. Okay, when we have something like this, so this is O of n operation and this is another O of n operation. So in that case, this is going to be big O of n plus big O of n. So if we remove the constants, okay, let me say for example, now we will now have 2 big O, we'll now have 2O, and we'll now have what? 2n. So if we remove the constant, this is going to give us what? O of n, which is the 2 and the 2 is going to cancel out. And if we cancel that out, it's going to give us what? O of n. So this is what? Removing constant. So we should what? Ignore constant. So if we have this O of n as many times as possible, this code is regarded as big O of n. The next big O notation we want to talk about is the big O of log n, which is the logarithmic time complexity. What are the criteria we'll see? Now, let us take them. So the first criteria is a single loop that depends on the input size, yes, but uses divide and conquer approach. All right, so let us go to the VS Code. Now, I have a function here which is binary search, and what this function is doing is what? It's accepting an array and a target. Okay, I want you to note something. It says what? A single loop, right? So this while loop here, so this is what? A loop. This is what? A loop. And if you look at the other part of the criteria, it says but uses divide and conquer approach. What is divide and conquer approach? Divide and conquer approach is dividing something, breaking down something into different or smaller units, right? So let us move forward. So it says inside the loop there is a divide and conquer approach. So let's look at the while loop. let us look at the while loop and let us see what's going on there. So if you look at the while loop, you will notice we have what? Left and right, which is defined, and we're using that left and right to divide the array. So this is the array and this is what the mid. So this is like the middle of the array. So what is happening here is we are dividing that array at each process. So this process is called what? Divide and conquer approach. All right. So it says an example includes binary search. This is an example of what? Binary search. Okay. We actually discussed this in the previous module. So if in case you want a detailed explanation and visualization, please ensure you visit the video. At the end of this video, there's going to be a playlist which will take you to the previous module. So like we said, we should not ignore constant. I hope you understand what we mean by constant. Constant mean if we have an algorithm in this code or in this code block that is the same big O of log n. So if we have multiple of these, if we have multiple of these in this code block, we should ignore what? The constant. The next big O notation we want to talk about is the big O of n log n. So what are the criteria of the linear arithmetic time complexity? What are we going to see that give us that understanding that this code is big O of n log n? So the first criteria is a combination of O of n and big O of log n. Okay, I want, if you can remember vividly, we talked about this in, I think, about some few minutes ago, and also the big O of n. So we've talked about the big O of n, we've talked about the criteria of big O of n, and we've also talked about the criteria of big O of n log n. So this big O of n log n is the combination of these two. All right, so the next criteria is a single loop that depends on the input n, right? So it depends on what? The input n. But another part of the code is what? A divide and conquer approach. If you remember, right, I just explained that the big O of n is what? Doing the divide and conquer approach, while the O of n is doing the linear operation. So this is the combination of both. So it says another part of the code is doing what? The divide and conquer approach. So an example include what? The merge sort and quick sort. All right, but for this video, I'm not going to give an example using merge sort or quick sort. We are going to get to that in the future, where we will talking about the different type of sorting algorithm. We are going to visualize and implement those algorithms. But let us look at this. If you look at this example, right? Okay, let me remove this group. If you look at this example, you can see what is going on. We have an input n, and n is a number. And what is going on here is we are looping by the range of the value of n, meaning n, which is 8, is the limit of the loop. And if you look at, there is another inner loop. There is another inner loop. And what is going on here is once we loop to this extent, right? So the second loop is doing half of what this of what the outer loop is doing. Okay. So what you will notice is the inner loop is not depending on the value of n. Rather, it is depending on the value of I. So the n you are seeing here is just the stop point for range. Right, it's just the stop point for what? For range. So start at this and end at n. J here you are saying is running like the half or more than half of the list. So but basically if you look at it, it is running like half of the input n. Is not running the same value as the value of n. So this algorithm can be labeled as the big O of n n log n. So the next big O notation we want to talk about is the big O of n raised to power 2, which is the quadratic time complexity. So what are the criteria we'll see? I want you to note that this operation is what n multiplied by what n. All right. So which is what a nested loop, right? So the most important criteria you will see is a nested loop iterating over the input data. Take note of this, iterating over what? The input data. All right, so if we go to the code, right? So I have this code here, which is counter norm is the name of the function, right? So what is going on here is we have an input, which is LST, and we are getting the length of what? LST. So we are getting the length of the list. And if you notice, right, so we are the outer loop is looping through the length of LST, which is the length, and also the inner loop is doing the same, right? So I want you to see the difference in the other one I show you. In the big O of n log n. Okay, yes. So in this example, right? So this one is not depending on the input size. Remember, I told you that this n is just a stop point, right? So this is starting from I and end at n. So this can also start from 2, can also start from 1, can start from even a number that is close to the value of n. All right, but when you look at the quadratic operation, both are depending on the input size. So, and that is what we've seen here. It says nested loop iteration over the input size. So both loop is what? Depending on the input size. So in this case, you should know that this algorithm is what? On raised to power 2, which is the quadratic time complexity. If you have another code like this, right? So this is what? O raised to power 2 plus O raised to power what? 2. So in this case, the 2 is going to cancel out and we are going to have what? Big O of n raised to power 2. The only case we can modify this to increase the big O notation is when we have a case like this. In this case, this is this is not a big O of n. Okay, let me write it somewhere more cleaner. So this is now O of n multiply by what? O of n, and multiply by what? Another O of n. So this is what? O of n operation. This is what? O of n operation, and this is another O of n operation. So the 3, which is O of n multiplied by O of n, will give us a total of O of n, right? Will give us what? 3O of n, right? Yes, will give us 3O of n, and n multiplied by n will give us what? N raised to power 3. This should give us n raised to power 3. So if we remove this 3O, right? So what we have is what? Big O of n raised to power 3. So this code is what? Big O of n raised to power what? 3. But let me just reverse everything back. So I'm just using it to give an example. So what we are seeing here is what? Big O of n raised to power 2. But if and only if this code is like this, so this is like O of n raised to power 2 plus O of n raised to power 2. So in this case, we are going to have two O's, and we are going to have what? N, sorry, 2n raised to power 2. So the 2 O going to cancel out, and when this cancel out, we'll be left with what? N raised to power what? 2. The next big O notation we want to talk about is the big O of n raised to power 3, which is the cubic time complexity. So how do we identify the big O of n raised to power 3? This is pretty straightforward. As you can see here, this is n multiplied by n, which give us what? The value of n raised to power 3. So this is triple nested loop iteration over the input data. This is also a brute force approach. Okay, so let us go to the code, right? So in my code editor, you will notice I have a function name called cubic time, and it has an input which is an array, and you can see the array here. So what is happening here is we are taking the length of the array as n, and we have what? A loop. So this is n, and this is what? Another n. So the whole 3 loop, which is the triple nested loop, is actually depending on the size of the input. So in this case, this algorithm can be regarded as what? Big O of n raised to power 3. The next big O notation we want to talk about is the big O of 2 raised to power n, which is the exponential time complexity. Mind you that this big O notation can be 3 raised to power n, can be 4 raised to power n, can be any number raised to power n. This big O notation is called exponential time complexity, but I'm using 2 raised to power n as an example. So this is an algorithm that multiplies the input by 2. Okay, so an example of this is what? Recursive exponential function. This is what a nested loop with what? Exponential function. It's also recursive backtracking. So let us look at the code example. So I am currently on my VS Code, and you can see this is a function that says generate a subset. So what is happening here is we have an element as an input, and you can see this is the input element. So the criteria for labeling this code, for labeling this algorithm as big O of 2 raised to power n, is this part of the code. Okay, this part of the code. So it multiply the input size by 2. Okay, so there is something more important here. So if I change this to 3, right? So this algorithm will be 3 raised to power n. Okay, so if I also change this to 4, this algorithm will be what? 4 raised to power n. But however, this is known as exponential time complexity. So do not forget that an algorithm with exponential time complexity, it multiplies the value of the input by the value of k. So I'm using 4 as my k for this example. The next big O notation I want to talk about is what? The big O of n factorial, which is the factorial time complexity. The first criteria you will see, which is the most important one, is the nested loop where the number of iteration of each loop depends on the input size. All right, so now I have a code example here. This is just one of the example. There are a whole lot of example. You can make research on your own. But what identify this code as the factorial time complexity is, if you look at the function, right? This is the name of the function, and it accepts an input. And if you notice, there is a recursion, and this is where the recursion is happening. So another thing I want you to notice is what? This is a loop, and the recursion is inside a loop. So the recursion is happening inside the loop, right? So the most important part of this code, and why this code is labeled as big O of n factorial, is there is a recursive call in the loop. Okay, so the fact that this recursive call is in a loop, this code is regarded as the big O of n factorial. So there are a lot of examples of the big O of n factorial. Examples like backtracking with exponential branching, exhaustive search. So, and there's another example which is a combination, solving combinatorial problem. You can see like this one here you are seeing, it prints out the combination of different numbers. So I'm going to run this code and it should print out results. So you can see we passed in just 3 elements, and you can see this is what it prints. It prints out 1 2 3 1 3 2 2 3 1. So it prints out all possible combination. So don't forget that this part of the code is what label this code, what label this algorithm as the big O of n factorial, because there is a loop, sorry, there is a recursive call in a loop. So the recursive call is depending on what? A loop. So right guys, thank you very much for watching. Please stay tuned. In the next video we are going to talk about the identification of space complexity. Thank you very much guys. I'll see you in another video.